So this is actually really cool to see everybody here. This is going to be a slightly different kind of presentation, very experimental, so I hope you'll bear with me. This is the singular slide from this presentation, and I'll spend the rest of the time sitting here banging away at code. So if you can't see me, I'm still here. Just listen to my voice and watch the terminal. So this is going to be hands-on category theory. That's maybe a little bit lofty of a goal. We're actually going to focus very specifically on how to do functional validation. So you may be familiar with validation from Scala Z or other types of validation frameworks where you can take values such as parsed JSON values or something, and then try to pass them into your server-side code, for example, and then do things with them. And you might have invalid or valid conditions that come out of that. So we're going to sort of dive into how we can build up a library that lets us do all that from scratch. But before we get there, if anyone wants to follow along or write the code as I write the code, you can go to this GitHub project, Scala Cats, under my GitHub account. And you'll see basically the exact same tutorial I'm about to walk through, but it's all spelled out. And so quickly before I jump into the terminal, just to get a better idea of where we're going, we want to be able to write code that looks like this. So we want to be able to write a parser that can return a possibly valid or invalid value, and then write a pure function that only operates on pure values and knows nothing about validation, but be able to map that function onto parsed values and apply it to additional parsed values. And so to get there, we're going to look at things like functors, semigroups, and applicative functors. We're also going to cover a few. Feel free to stop me at any point. There's going to be a lot of interesting Scala features that we sort of touch on, but I won't spend much time covering in depth. But things like algebraic data types, type lambdas, hierarchy-kinded types, implicit conversions, type classes, and so forth. Cool. So let's put this to the side. Yeah, question?
So the fact that you're using some special symbols for division and multiplication.
So the question is about these symbols. This is not meant to mean multiplication or division. These are just operators that have kind of a funny syntax. And the syntax is inspired by Haskell and some other places. But we'll see later that this actually means map, and this means apply from functors and applicatives.
Okay.
All right, so I'll just put this to the side. We might come back to it if I need to copy-paste any code. And I want to make sure the font is going to work for us. So let's actually remove that. Start from scratch. OK. So is that visible at all? No? OK. Let's try changing our color scheme here. Something a little bit more readable. Anyone know OS X and why that didn't work?
That's just setting the config. You have to sort of apply it to the window.
Is there an apply button?
No, just go back to a window. You have to like pick which speed.
Oh, gotcha.
Yeah.
OK. How's that? A little better? Cool. All right, so let's start at the start. Imagine that we want to build something like a web service where we're trying to bridge two worlds between our clients who are living across some HTTP channel and our server where we have full control over all the code we write. And in an ideal world, we have very nice, clean, pure, referentially transparent server code, but our web world is not so constrained. And so since our clients are going to be accessing our services over HTTP, there could be all kinds of problems with their method invocations. They could send bad data or invalid data or malicious data or even no data. And so these are all cases that we have to handle. But we want to figure out some way to cleanly bridge the gap between these two worlds so that the process that we end up taking for validation doesn't sort of leak into the server code that doesn't care about validation. So let's start with a very simple imaginary method that we want to expose as some kind of a service to some unsafe world. So we'll write an absolute value function. So absolute value has the following type. So absolute value is a function that takes an int and returns an int. And for our implementation, we'll just steal it from Scala. OK. And hopefully, I can have, at this resolution, a couple of windows side by side. We'll see if it works. I may want to do them vertically, actually. Let's try this. Oops. Let's see how that works for us. So in parallel, I'm going to be editing this text file, Scala, cats.scala, and then interpreting it in the Scala REPL. So there's our file, and we'll run Scala. And so I will periodically be loading this file to make sure it compiles and then to also interact with it. Cool, so there's our abs function, so we can test it out with a negative number. And so that seems to be working. So now let's write, so imagine that we want to expose this to a world where data is potentially invalid. So let's write some sort of parser that can take data from that world and then return something that's a little bit safer to use. So we're going to write a parser. So this takes a string. And it needs to return something that can be either valid or invalid. So we'll use Scala's either type for this. And either, if you're not familiar with either, either is an abstract class that has exactly two implementations called left and right. And there's really nothing special or magical about them. They're just boxes that hold a single value and are distinguishable by type. It's either a left or it's a right. And that's pretty much where the specialization ends. By convention, when we're using either to represent things that can fail or things that can be valid or invalid, we tend to use left to wrap invalid values and right to wrap valid values. But again, that's just convention, and it really doesn't matter. But for this demonstration, we will use that convention. So on the left, if our input fails to parse as an integer, we'll return some string containing a message about the failure. Otherwise, we'll return the successfully parsed integer. And we'll do this with a simple try-catch. So we'll say x.toInt. And so this is returning an integer, but up here we see our function returns an either, so we have to wrap this in a right. And x.toInt could potentially throw an exception. If, for example, we try to call toInt on a string that is not parsable as an integer, it will throw some kind of number format exception. So let's just catch any kind of exception and say, if any exception is thrown or any throwable is thrown, we'll just say, well, we don't know what to do. Thanks. All right, so let's make sure my syntax is correct. So now we've got two functions, abs and a to I. And so I can call a to I like this. Pass it a string. And since the string 1, 0 parses as the integer 10, I get back a right containing that 10. If I were to pass it something that is not parsable, we get back a left containing the message 10 is not an integer, or at least as far as x.toInt understands. So now we have a way to take input from the user, where that's represented by a direct call to this a to I, and get some sort of output that might be valid or might be invalid. But we don't have to worry about any exceptions being thrown or anything like that. We also have a service function, which is a pure function int to int, that we want to put together. So we could do this with a pattern match. We could call a to I and get back an either like we did here. And and then pattern match on that, and if it's a right, pass it to the abs function and return the result, or if it's a left, just return the fact that it failed. That's a little bit more verbose than we'd like. What we're really after is a single line way to apply one to the other. So what we actually need is a functor. And so you're probably, whether or not you know it, you're probably familiar with what functors are. If you've ever done something like this, so if we have list of some integers, and you call the map function on that list, and you pass it some function that takes an integer and returns something. So we'll just say x plus 1. The instance will take that function x plus 1 and apply it to every element in the list and then return a new list containing those elements. And even though Scala doesn't have a trait called functor, it's basically the same shape. And so we're just going to make it more explicitly declared here. So let's start with a trait called functor. And it's got a couple type variables, which I'll come back to in just a minute. So a functor is anything that defines the following method for our purposes. So it's a map function that takes some function from A to B and returns a new f of b. So what's going on here? We have a trait that's abstracted over two types. A is pretty simple. A is just some arbitrary type. F has this syntax, which means that f is some unary type constructor. It's a type that itself needs another type to emit a type. So for example, basic Scala collections like list or option or set or whatever are each type constructors that take a single type. So I couldn't really have a list of something like this because if we want to forget about type erasure and Java 4 compatibility, there is no such thing as a list. It's always a list of something. So we would say a list of integers is, and it'd be nice if I got my syntax correct. So if I say val x is a list of integers, and then I give it some value. Right, so in this case, list is corresponds to our f, because it is a type constructor that takes a single type variable. So then when we define our map function, we're basically saying that there's some type constructor, list for example, that contains things. And in this case, it will be a thing of type A, that we can pass a function from A to B, and then our output will be whatever that type constructor was, but with the B type. So in this example here, we have a list of integers. And so you can imagine f is list and a is int. And we're passing in a function which is just int to int. And so our output is list of int, where b is int. And so as I said, we want to, we're playing with the either data type here. So we have our parser function, which returns an either. So what we need to do is build an either functor. And if you're following along on the GitHub page, you'll see some diagrams that show sort of how you can imagine the categories of types and the categories of lifted types, and then what map is doing when we're transforming a function from one category to the other. It's a little bit too hard to describe with words, so I'll just skip it and allow you to read that later. But let's write our either functor. So I want to, just to make this easy to use, I'll put it in an implicit conversion so that we can automatically add this map function onto any instance of either. Okay, so this is an implicit function that takes any either. And the reason I'm using these type variables is we will want to use the a later for our a to b function. But z is sort of our error case. It's our invalid case. So it's not going to change. And you'll see that demonstrated shortly. So our implicit conversion takes an either, and it returns a new functor of type A. And then here it starts to get actually a little bit tricky. So as I said, we need a functor has these two type variables. One of them is a type constructor, which itself needs a single type. Either is a type constructor which needs two types, so it doesn't really fit the shape of the problem that we're trying to solve. But as I said, with validation, our error type doesn't really change over time, but our success type might change. Just like with list.map, you could get a new list of strings or a new list of something else that wasn't what you started with. So for example, we had this function before. We could just say x.toString. And a result, so we went from list of int to list of string. And so we'll do something similar with either. We know z will never change, so what we really want is to constrain.
Sorry, that's this.
Yeah.
You're saying that the failure does not change. But
Mhm.
wouldn't you, if you change the types, the kind of exception that you're going to get is going to be different? Or you're abstracting failure as a failure?
We're abstracting failure as a left of whatever we started with. So in this case, failure is always a left of string. And we have some.
Exception, and that's it. Stop.
Well, the exception could trigger the failure, but the way we're representing it from our parser would be a left of string.
Oh. So as long as it's left, it doesn't change. That's why it's left.
Right. As long as once we've got a left, we have a failure, so there's really nothing we can do further. So it will always stay a left of string.
Chain of, you're going to chain stuff, right? You're going to do the.
We'll get there, yeah. Yep.
So does the failure change in any of the consecutive either's?
The failure will not change type, but you'll see when we get to applicatives that it will change its value.
Okay.
And we'll see how that works in just a minute. OK, so what we really want to do is constrain z. So say our f type is always an either of z or something, where something can change. Scala doesn't allow this syntax, so to get the same kind of thing, we need to use a type lambda. And the way we do that is declare a new type. So we will call our new type either z, and give it an arbitrary type variable. So an either z is an either of z, or b. And then the way we reference this thing is with this hash z. So this is a little bit noisy, but what it means is that our f of something is really an either of z or something, whatever something might be. So Functor defines map, so we'll do that. So remember, map takes a function from a to b and returns whatever type we're lifting into a functor. So in our case, that's an either of z or b. So we're basically adding a function, map, that given an either za and a function a to b will give us an either zb. So if we have a left, yeah?
Really quick question. Is it possible to move the type alias outside of the, like above, so it looks less noisy?
So the question is, can we move the type alias to clean up the code a little bit? I think we could put it in an object somewhere, but I'm just declaring it inline here for demonstration. All right, so we know that our x is an either, so it has one of two types. It's either a left or a right. So let's do a pattern match. So if we're starting with a valid value, a right, then we have some value. Actually, let me make this more clear. We have some a to which we can apply the function f. So we'll return that in a new right. On the other hand, if we're starting with an invalid value, there's really nothing we can do with it. We have a z for some type z, and we have a function a to b, so we can't apply that function to the z. Really, the only thing we can do is pass that thing directly through. So we'll just return a new left of the same thing. All right. I could write an @ sign, right? I could do something like that. Same idea. So let's make sure that this compiles. Oh, yeah. OK. So now we've got an either functor, which is a way to add a map function to any arbitrary either. Question?
Just so I understand scope of this type lambda with either Z that we have, would you be able to have the return type of map be either Z or B, or is that name not bound outside of this particular?
The question is, for this type lambda, we're creating an either Z, but the thing we're returning is not an either Z. Well, it sort of is, but not by name. It's an either of Z, B. Really, that's just a side effect of how we've chosen to define our functor trait. So our functor it could return a functor. It could go from functor to functor. In our case, we want to go back down to the either type because that's where we started and that's kind of where we want to end up. And then since we have our conversion, we can lift that back up to the either functor if we need to apply map again. So that's kind of a non-answer. Really, this is just the one way to implement it. Scala Z does it slightly different, where their functor type declares something like this, I think, rather than in the trait. It's just two ways of skinning a cat.
So it's not that they're equivalent, and either Z or B is equivalent to either of Z and B?
Define equivalence. So I'm not sure if the type system would consider them equivalent for like a dot equals or an equals equals, but semantically they're equivalent. I mean, it's just a type alias. So I think like in Scala, if you create a type alias, foo equals string, Scala considers a foo to be a string, but I don't know if it considers a string to be a foo. I'm not quite familiar with that.
You can't instantiate the alias.
You can't.
Only match it.
You can't instantiate the alias. Okay. So maybe. I'm not sure. But let's press forward. We can see this thing in action. So what we want is an either that we can create and turn into a functor, and then lift up our abs function and then apply the two. So let's parse an integer. Actually, let's make it negative so we're actually seeing abs work. So there's our either. And if we call map now, we will invoke this either functor so that we're pimping the map function onto that either. And then we can pass it. So we have an either of string int. So we have an either of string int. So our a is an int. So we can call map and pass a function from int to whatever we want. So we'll pass abs. And so the result is to lift this function, f of a to b, into the either functor so that it can be applied to the value that's inside. Or not. If we started from an unparsable value like this, and then we tried to map our absolute value function, we would just end up with the same error message. And so it's kind of a no-op. And that's because we matched on this second case. And then one further thing before we move on to applicatives is it's sometimes useful, and it will be especially so more toward the end of this talk, to be able to do this in reverse. So we're starting with an argument that is an either. And we want to lift it into an either functor so that we can apply a function, so that we can lift a function and then apply that argument to that function. It's sometimes nice to be able to do that in reverse. So we start with the function and we implicitly lift that so that it's ready for an argument that is contained in an either, and then they can be applied. So let's write that code.
I'm sorry, so the goal here is basically, if I'm correct, is at the level of validation.
Yes.
That's what we're trying
Yes,
to
the goal is to do validation.
Okay.
But the goal is to do validation, but to keep the validation logic completely separate from our server logic. So I haven't modified the absolute value function to understand validation. It just takes an integer. It doesn't take an either string int. That's really the key. And then later we'll be able to compose these things together, but still without worrying about validation on the server side. So we want to be able to lift any function, such as absolute value, into something that has this funny looking method. So all this is doing is what we did below, but we're starting with the function and we're lifting that up before we have the argument to apply. So let's make sure I type that right. Cool. So we had this construct before. Now we could do just syntactically the reverse of that. So I can say absolute value and then map that function onto a parsed value. And we get the same result. So any questions before we move on to applicatives? Yeah.
So when we specify that functor, we said f and then underscore, right, in the bracket. Could we specify there the capitalized A because we know that the type will be the same as the left argument?
Can you repeat that? I don't quite understand.
Let's scroll up there. I'll show the code.
Oh, whoops.
Yeah, yeah, right here. Could we specify instead of the underscore, f underscore, could we specify the A there? Because the type.
I see. So the question is, can we say f of a right here? No. To say f of a would mean that we're always using an either string int, but it's possible that the result of mapping could change the type of that either.
So this is the resulting type, not the type of the argument.
This is the type constructor to use. So f of underscore is not quite yet a type. It's like list.
Yeah, but the underscore means any type, right?
The underscore, this is just the syntax for saying we want to use the type, we want to use f, which is a type constructor of a single type variable. This is just Scala syntax for saying that. So this is just a way to tell Scala that f is a type variable, but by the way, it's a higher kind of type where it takes one type variable.
Like a template.
What's that?
Like a template in like another language.
It could be. I don't know templates. OK. So I'm going to comment some of this out. Since we're just in the REPL, I don't have nice namespaces. And then I'm going to quit the REPL and start it again. And that's just because I want to clear out the implicit conversions from memory. OK. So let's look at a slightly more complicated function. This will be an addition function between two integers. So this is a function that takes two ints and returns another int. So it should be straightforward. OK, so the function add2 takes an x and a y, and it returns the result of x plus y. So if we want to follow the same kind of process where x and y are both inputs provided by a client, and they need to be validated, they could be invalid values, this starts to get much more tricky because we would now call a to I on both of those inputs and come out with two eithers. So we would have x, which is some parsed value, which might be a right or a left, and y, which is another parsed value, which also might be a right or a left. And so we can't call map on one of those and apply add2 because we lose track of the second one. So a functor won't quite get us where we need to go. We need an applicative functor. So an applicative functor builds on a functor by adding a new function called app. So let's, actually, I'm going to go up above here. So here's our functor trait. An applicative, it looks almost the same. And it extends functor. And so to build on your question before, this is how we tell Scala that our f of underscore is this f of underscore. So in this case, we don't have to pass the underscore. It's just an implementation detail of the semantics of the syntax. Could you really? Oh, OK. I don't think you could do this. I think that would not compile because it wants a concrete type. And so our concrete type is this type constructor. But I could be wrong. I also have no idea what I'm doing. So cool. So let's build on our functor. We already have map because we're extending functor. So let's add app. And by the way, the names of these functions are largely historical in nature. So app looks almost the same as map, with a key difference. Rather than taking a function a to b, it takes a function that's already been lifted into the functor of a to b, and still returns an f of b, the same kind of type. So map and app return the same thing, and they start from the same place. But the argument that they take is either a function in the category of types or a function in the lifted category of ethers in this case. And we'll see. Whoops, I need a b there. We'll see what that looks like in just a sec. So there's actually quite a lot of code for me to type here, and I'm running low on time, so I'm going to cheat and copy and paste it. And then I'll go over what I just did. Oh, so actually, before I get there, we want to, since we're now parsing 2 input values and then potentially producing a result, there could be potentially 2 error messages, right? If both x and y failed to parse, we would want to know about both of those failures. And so think if you're building a web service and maybe you're interacting with JSON or you're taking a form submission from a user, you want to be able to validate that whole thing all at once and then know everything about it that failed, and not just know a binary state like either it failed or it's good to go. So we're going to change our either type a little bit to be either a list of all of the error messages, all the things that went wrong, or the successful final result. And so this doesn't change much. This is just we insert a list there. But before we implement our either applicative, we also would like to keep this thing nice and generic. There's nothing inherent in applicatives that should bind us to Scala's list API. So we'd like to generalize the notion of things that can be appended. So a list is something that can be appended. I can take one list and concatenate it with another list with the ++ operator. But that's really a general property called semigroup. So semigroup is any type that can be appended to itself and return the same type. So a list appended to another list gives you a list, for example. So if we take an A, we should return a new A. And so let's make a list semigroup so that we can use this append syntax generically instead of list dot ++ or something very specific. So we want to be able to convert a list of A's into a semigroup of a list of A's. And so that way we can implement append, which takes a new, let's call this X, a new list of A's, and returns the concatenation of the 2. Make sure that compiles. Looks good. So what does that look like? If we have a list of 1, 2, 3, with Scala we could say ++ list 4, 5, 6. But with this implicit conversion, we can also say now append. And append will take our list, convert it into a semigroup of list, which now has an append function that takes another list and returns a list. So really, append is kind of like a synonym for ++ in the list case. And then you can imagine other things that would be appendable, maps or arrays or any kind of collections. Or even a string might be an appendable sequence of characters. But for our purpose, we just need lists of strings for our error messages. OK, so now I think we can, now we can build our either applicative. And this one's pretty long, so let me just copy here and save time. And then I'll go over what we're doing. So if you remember, let me go to the top here. An applicative is a functor with this extra function app. So if we look at our either applicative, we define map, and that's actually the exact same implementation as we had before, but I've commented it out, so there's no code sharing But explicitly, we have the same kind of construct. We have the same type lambda that we saw before. So we need to constrain that z type, which is now going to be list of string instead of string as it was before. And we're lifting up an either where it has some error type, which in our case is list of string, and some data type that we'll be manipulating. We also need to add this implicit here. We don't want our parser to worry about semigroups directly. We just want to deal with things that can be turned into semigroups. So our parser returns either list string or int. But for us to be able to use a list of string as a semigroup, we have to also pass in an implicit conversion for whatever that z type is into a semigroup. And so that way, later, if I am working with a z down here in this code, I can convert it into a semigroup and call append. OK, so I'll skip over map because that has the exact same implementation we had before. And let's look at app. So what have we got here? We have a parsed value that the user passed in. So that might be a right or a left. And then we have some function that has been lifted into an either. So this could be a left of a list of error messages or a right of a function that we want to apply to the input if it's valid. So we actually have 4 conditions we need to worry about. X can be left or right, F can be left or right, and we need to have take care of all 4 combinations. So let's first look at x. X is our input value that was returned by a parser. So if our parser gave us an error, so it gave us a left with a list of error messages, then we know our output is also going to be an error because our data is either valid or invalid. And once it's invalid, it will always be invalid. So we look at the function that we've lifted, which itself could be an invalid or a valid, a left or a right. And if it is also a left, we need to take the error messages it knows about and append those to the error messages that the parsed value knows about so that we're not losing any data. So if that's the case, we return a new left with all of those error messages appended together. And so this is where our semigroup implicit conversion gets utilized. If we were explicitly using lists throughout this, and maybe I should have done that just for simplicity for this presentation, but we could have just said L plus plus L2 if these were lists. But as it is, L is just any generic type that can be converted to a semigroup. If, on the other hand, the function that we want to apply is some valid, it's a right of the function, that means we have a right of a function a to b, and we have a left of a list of messages. There's really nothing we can do. We can't combine these in any way. So we just pass our x value, which is a left of L, directly through. There's nothing we can do. So we kind of drop the function on the floor. So that's if our input value, the thing that was parsed, is invalid. If, on the other hand, it's valid, meaning it's a right, we might be able to use it. So f is the function that has been lifted. F could be an invalid value. It could be a left, in which case we're in the same situation. We have, but with the types reversed. We have an int in our case, and a function, and a left of a list of messages. So there's nothing we can do with that int that's meaningful. So we just pass through that same list of error messages. Finally, if we have an input value that's good and a lifted function that's also good, we can apply it, which is what we really want. So R2 is our function from A to B. It's this guy. And so we take that function and we apply it to the valid input value, and then we evaluate that and then return it all in a right. So that's kind of a mouthful and a bit of a fire hose, but let's see if we can put that to some use. So first let's look at, we already looked at the list semigroup. So let's look at the either applicative. So we have our add2 function, which takes 2 numbers and adds them. And we have our parser, which takes a string and returns either the parse value or an error message. So how can we put all this together to parse 2 input values and then send those off to our add2 function and then maybe get a valid result? Well, it looks a little bit like this. we parse a value, and then we map it onto the add2 function. And what does that give us? That gives us this kind of complicated looking thing. It's an either where it might be the list of error messages, or it might be a function int to int. Well, what the heck is this function? That means that if this thing parsed correctly, it partially applied add2 with the value 22. And the result of that would be another function that's waiting for y so that it can add 22 to y and then return the result. So the result of calling this is an either that might be a list of error messages, or it might be more code to execute. And so we can send another input value off to that function, if it indeed is a function, with the app method. So let's parse another value and call app, and then send it off to whatever this thing returns. And so there's the result of 20 plus 22. And so if either one of these were unparsable, we would get a list of all of the errors. So in this case, there's one error, a is not an integer. And if we had two errors, we would get a is not an integer, b is not an integer. So you can imagine if this were being applied to something more complicated, like form validation or JSON parsing, we could collect up a list of everything that's wrong as far as our validator is concerned. But we're not quite done yet, because this syntax is a little bit tricky, and we have to get our parentheses right, and we have to know that because of the way that app applies, it must take something that is an either of list of string and function. So it's kind of confusing to get the order right. Furthermore, the function it appears last in our syntax, which is maybe kind of annoying. It might be nice to have it on the left. Yeah.
I'm using Scala 210.
This is Scala 210. Yeah.
2.9 doesn't work.
Let's talk afterward, because I'd actually like to see what 2.9 chokes on. So we're going to go back to that funny % operator that we had before that let us turn Functor around, and add another one that lets us turn app around as well. So we'll have basically what we had before, but slightly adapted to know about semigroups. So this lifts a function, g to b, such that we can apply we can map it onto some input value with the restriction that z must be able to be turned into a semigroup. I think that's about right. I'll just double check that compiles. Yep. All right, so that's basically the same mapper that we had before, except we've added this implicit conversion so that we can use these semigroup Z types. So now let's do the same thing for the app operator. So this will be a little bit more complicated, but not terribly so. So in the case that we have an either Z or A to B, like we had midway through that process that we saw before, and we have a way to use a semigroup, then define a function called this thing, which is sort of a, I don't know, an asterisk in angle brackets, and that takes an input value that has been parsed, which might be applicable to this function. And let's double check that compiles. Cool. So what does that give us? Well, the last thing we did was this. Oh, sorry, let's see some actual numbers. The last thing we did was parse two values, take the first value and apply it to this thing that's returned by mapping this parsed value onto the add function. Now we can turn the whole thing around and say add2, and then onto that function map the value returned by parsing the string 20, and then onto that function apply or app the last value. And there we go. So we get 42, just like we did in this case. There is a key difference, though. So let's look at, again, unparsable values. So if we have a and b, we get a list of error messages. A is not an integer, b is not an integer. If we use this syntax, a and b, you'll see that the error messages are actually reversed. So we have list b is not an integer, a is not an integer. And that's simply a function of the order in which the application is happening because of these conversions. But it is something to take note of. And so finally, I mentioned composition at the beginning. So now we have sort of a nice clean way to do both validation and application together. And then, of course, if this were an actual web service I were writing, I would have logic that would take the result of this, and if it's a valid value, if it's a right, send it back to the user, and if it's a left, build some error message and send an HTTP status code 400 or something like that. But as it is, we have a right or a left as the output of this. But we can also start to compose these things. So let's say we want to call add2 and abs together. So we want to say add2, and then onto that map the result of mapping abs1 or abs onto a parsed value. And so this should give us an either that's ready for the next argument, just like we had before. And so we can say a to I of 22. And there we go. And so now we can start to compose these things. And it stays somewhat readable as long as you remember that this percent operator, which could be more appropriately named, means this is something that needs to be mapped, and this star operator means this is an already lifted function that needs to be apped. And I think that's about as far as I wanted to take that. So are there any questions? Yeah.
Scala Z has this notion of applicative builder. And so it seems like that builds up the applicative and then calls app on it. Is that correct?
So you're talking about Scala Z's applicative builder?
Yeah, they have a syntax that seems like the opposite of this. It builds up the applicative incrementally first, and then you call app as a result.
So the question is, Scala Z's applicative builder lets you build up the applicative and then call app on the result. And I haven't worked with that, so I'm not quite sure. But with applicatives, you need to call app every time you want to apply a function that has been lifted. So I'm not quite sure how that works in particular. It sounds like it might be similar to this syntax, but I'm not quite sure. Scala Z does this slightly differently, as I touched on, where the functor and applicative traits are defined with an explicit starting type. So you would say, rather than saying a functor is anything with a map function, in Scala Z they say a functor is anything with a map function that takes the type constructed value f of a and the function a to b and returns the f of b. So it's slightly different, and it's actually a little bit better in the way it constrains what you're turning into a functor. But I like this as a way to reason about what the functor does, which is map over things.
Do you have any kind of production examples of applying this kind of technique?
So examples of applying this in production, we use something similar to this to do validation on our web services, where we have multiple functions that might succeed or fail that need to be composed like this. And by composing them together, we let those, we get to lift these pure functions into this validatable world without having to do lots of pattern matching and if right then this, if left then that. That's all kind of abstracted from our server-side code. So I can't point to anything on the web that would explicitly demonstrate this, but it is in use basically, this is directly applicable as is on any kind of REST API or anything that takes unsanitized input.
And it would be very, very valuable to see a non-trivial example.
Yeah, I agree. So the question is, it would be valuable to see a non-trivial example. I wanted to take this all the way to a web application, but unfortunately, that would take far more time. So we have this simple trivial example. Yeah? Is there a connection between applicatives and concurrency? Yes. One thing that may not have been clear is that this A2I and this A2I invocation are not dependent upon each other. They both produce an either as a result. So they could actually run in parallel, and this whole line could be deferred until all of the results are there. We could also make it a little bit smarter, I suppose, that if the first failure that occurs might end the execution of the others. I'm not sure. I haven't really played with that. But certainly the evaluation order does not matter of all of these arguments. And so that's slightly different than something like a monad, where you have to do the next step depends very specifically on the result of this step.
Sorry, the percent operator is associative?
Say that again?
Associative, the percent operator?
The percent operator is associative. The star operator is associative. Because that's our apply function. Percent, let's see. So percent is map, which we would really, I think we would only call that once in this example. So I'm not sure, I can't think of an example where we would have two. Oh, so you're talking about this one. Yeah. Let's see. That's a good question. So actually, not quite. So it's actually this operator that has associativity, I think. And then, because remember, we have to do all of this. And then finally, when we have our lifted values, can we apply it to the function? So this is actually happening last. We're just writing it first because it kind of makes more intuitive sense. So I think I'll take any other questions during the break. Because I'm getting the red light. So thank you, everybody.